All right, we're going to talk about the Newton-Raphson root finding algorithm today. So, what root finding is finding the roots of an equation, obviously, but the roots are where a curve crosses the x-axis, or you may call them like the zeros of an equation. So, I've got this as an example equation. This is just a polynomial quadratic equation. And if I were to graph this, I plugged in some random, just some x points, and then this is the y equation here. So if I were to plot this in a scatter plot, it would look something like this. So if you were to try to find the roots or the zeros, whatever you want to call them, the answer you'd come up with would be these points right here. So it looks like -5-ish and 8 or 9 or so. Now you could do that pretty easily with this using the quadratic equation. -b plus or minus square root of 4ac all over 2a. You remember that. However, it becomes a challenge to find the roots if you're to throw in a term like x cubed. Now what that does, if I were to throw this in my equation here and drag that guy down, now my curve looks something like this. And there's no way to solve for x algebraically if I were to set this equation to 0. If I were to set y equal to 0, there's no way I can solve for x algebraically. And I could look at the curve and maybe find manually where it crosses the x-axis. This is not very clear in this drawing here. Or you could do something like guess and check, where you just continually guess values of x until you get 0. That's going to be really difficult and take a long time unless you're a genius. So what the Newton-Raphson algorithm does is it's basically a guess and check method, but when you follow the steps of this algorithm, the guesses that you're plugging into this equation become closer and closer to the actual guess. And the way it works, let me do some scribbles on the graph here to show you kind of how it works. You start out by guessing what the answer is. So you'll plug out, you'll take a guess of what you think the root is. You want to be fairly close, and we'll talk about later what happens if your guess is far off. But let's just say, for example, I guess the root is 25, which is this guy. You plug in a guess, and if the answer is not 0, so if you plug it in and y is not 0, what you do is you draw a tangent line here, a line that's tangent to the curve. That was a pretty bad drawing. It's got to touch it. It's got to just touch it. And then you find where that tangent line crosses the x-axis, and that becomes your next guess. So now you plug that in to your y equals equation, plot it, or not plot it, but see what you get. And if it's not 0, you draw the tangent line again, and you plug in this next x guess. And then that process will repeat until eventually one of the x values that you plug in is going to give you 0 as a result. Now, I'm actually not sure where our 0 is here. It's going to be kind of somewhere in this region. But we'll actually numerically solve that here right now. So let me get rid of my chicken scratch. You saw kind of visually how the algorithm works. Now let's do it in a table here. So the first thing we did was we plugged in a guess for what we thought x was. So I'm going to have a column here called x guess, and I'm going to make a table of all of our different guesses here. So the first one is x guess. We'll plug in 25 again. And then let's evaluate what that is in this column. So y of x guess. And that's going to be equal to, it's like just plugging it into this equation here. So x to the third plus x squared minus 3x. I hate when Excel does that where it gets in the way. Minus 50. So obviously that is not equal to 0. So that means we got to draw a tangent line and see where it crosses the x-axis. So to do that tangent line, the first thing we're going to need is the slope of that tangent line. And one way you can get the slope is you can take the derivative of this equation and plug in your x guess. That would tell you the slope at that point. But a lot of times you're doing Newton-Raphson on some wild equations where it's not easy to take a derivative, okay? So the easier way to take a slope is to manually find what the rise over run is at that point. And you can do that by plugging in a number that's just very, very slightly bigger than x guess. And then you take the result of that minus your y of x guess. And that's going to be the rise, and then divided by the run. The run is going to be the amount bigger than the x guess. So let's do it, and hopefully this makes more sense. We're going to call our tiny little amount greater than x guess, we're going to call it dx. Usually in calculus, anytime you see d in front of something, it means very small. That's what I think of. And that very small number, I don't count the zeros here. It's just going to be 0.000001. And so let's manually find what the rise over run is if we were to plug in that. So it's going to be x guess plus that dx to the third power plus x guess plus dx squared. And if you're not familiar with Excel, you put the dollar signs in here so you can drag this formula down to multiple cells, and it'll keep referencing this cell here. Minus 3x plus dx minus 50. So that looks like the same value as our x guess, but it's actually very, very, very slightly bigger. So what I'm going to do is take that equation that I just plugged in minus the y of guess that I just got, and I'm going to take that difference divided by this little dx term here. And that's roughly or very close to what the actual slope is at that point on my curve. Okay, so now that we know what the slope is there, we know the slope of our tangent line, we've got to figure out where that tangent line would cross the x-axis. So to do that, we're going to have to do a little bit of algebra. So I'm going to bust out my pen. We know for a straight line, y equals mx plus b, where m is our slope, b is the y-intercept. We know the slope because we just calculated it. We know when we plug in x guess, which was 25 for our first case, we know what y is equal to. So that lets us solve for b here. And I'm just going to real quick say b equals y guess minus mx guess, where m is that slope that we just calculated. So once we know b, the equation of our line is kind of defined. So we want to find where that line crosses the x-axis, and it crosses the x-axis when y is equal to 0. So if I say 0 equals mx plus b, again, we know the slope. The slope of that line doesn't change. We know b because we just solved for it. X is what we're trying to solve for. So we do a little bit of algebra here. We say x equals negative b over m. And then let's plug in what we got for b back up there, back down here. So we can say x equals negative y guess minus m. I should call this like y of x guess minus m times x guess. That's b. It should be negative b actually, so I'm going to do this. Actually, I'm going to rewrite the whole thing because that was nasty looking. X equals negative b, which was y of x guess, the first x guess that we did, minus m times x sub guess, all over m, which we know. And then if we one more time simplify this, we get negative y of, I'm just going to call it y guess again because it's shorter, over m plus, because these negative signs will cancel out and make a plus. These m's will cancel out, and we just get x guess. So that is our x, where the tangent line crosses the x-axis, and that's going to be our next guess in the algorithm. So I'm just going to call that x next. And that's what I'll do in the table here too. So x next equals, I'm just going to use this same equation we derived here, negative y of guess divided by slope plus our x guess. Cool. Now we can see if we're to plug that in. I'm just going to steal this equation here. Y of x next. The reason I'm plugging that in again is I want to see, does it equal 0 now? Because if it does, we're done. So if that equals 0, then yes, we're done. Otherwise, you got to keep going. So nope, not done. Keep going. This should go a little bit faster now. So our x guessed is just going to be our next that we previously found. And then all of these equations above should be exactly the same. I can just pull these down. And that process is just going to repeat itself. And you'll see that our guess is, the result of our guess is slowly getting closer to 0. Very close. There we go. So the root of that equation was 3.6. And then you'd be done. So you converge to a 0 there. That is the Newton-Raphson root finding method in action. So the reason that that's useful is, you might be looking at this and saying, who cares? Why do I need to find a root? Well, it's useful because a lot of times you'll have an equation like this. You'll have some kind of curve. And if you plug in x values, you can find the y value all day long. But a lot of times it's the case where you know a y value that you want to get, and you need to figure out what x value you need to plug in to get that. So as an example, let's say I want my y to equal 100. What x do I need to plug in to get that? Well, what you could do is just subtract that 100 over to this side of the equation. So you get 0 equals, I'm just going to copy that. 0 equals x cubed plus x squared minus 3x minus 150. So now if I update my equations to reflect that, basically what I can do now is my root finding algorithm. So change that to 150. That needs to be changed to 150. And that does as well. So if I were to now drag that formula down, it should, that equals x next. That converges. So if I wanted my y equals x cubed plus x squared minus 3x minus 50 to equal 100, I would have to plug in 5.176. That's the power of root finding. And this is kind of a clean looking equation here, but sometimes you'll get a nasty one where it's like 1 over, square root of y plus y to the power of x equals x cubed, blah, 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 blah. And what you can always do is just take one side of the equation and subtract it over to the other side so that you get 0 equals some big nasty equation, and then do your root finding process. So that's going to be it for the Newton-Raphson root finding algorithm for today. If you have any questions, please leave a comment below and I'll do my best to answer. Otherwise, I'll see you in the next one.